Good morning, everyone, and thank you for joining me for the Zak Virtual Festival of Facades. My name is Mike Picco with Picco Engineering, President and CEO. Picco Engineering was established in 1992, a structural engineering firm with three main pillars of work: stone, structural, and residential. Our primary focus really is involved with stone cladding and cladding of different types on buildings. Our scope of work includes anything from consulting to design assist, shop drawing, anchor details, forensic engineering, anything related to cladding, and primarily with natural stone. Some of the projects that we've worked on in the past are the Canadian Museum of Human Rights, where we used backlit alabaster on a series of galleries, ramps that connect galleries. The Aga Khan Park in Toronto utilized granite exterior cladding on one building and limestone on another. And the Ark of Return, the United Nations Memorial in New York, which used, incidentally, the same marble that we're using on our case study today. So today we're going to talk to you about the Museum of Fine Arts in Montreal, where we utilize the marble cladding in a very unique way. So I'll give you start with the project background, and I'll talk to you about the coring and sourcing. We'll talk about testing and shop drawings and the importance of that on a project like this. We'll review the anchor design and the approach we took on this project. And then finally, the project team, and I'll end with some final photos of the project. So let's start with a little bit about the project background. The Montreal Museum of Fine Arts was founded in the 1800s and moved to its first permanent location in 1913. It was primarily that single building till the early 1990s, where an addition was built, and then some aggressive, more structures were added. And now the museum consists of 5 different pavilions at this point. Historically, the material used was the Danby Vermont marble, and the architect's goal was to try and make this the same material on the new pavilion that we were working on. So the inspiration that the architect was trying to achieve was to try and mimic the quarry walls onto the new building. The new building was up against an old historic cathedral, which was purchased and became part of the museum. But the goal was to try and replicate the quarry walls as much as possible. That was the initial goal. And we're marrying a very modern part of a new building with the historic buildings adjacent to it, which are part of the building, part of the museum, and really stark contrast to the old buildings. The museum won several awards for the design of the building. The Terrazzo Tile and Marble Association of Canada was the Project of the Year in 2012. Hard Surface Award also with the Terrazzo Tile and Marble Association. Urban Architecture Award in 2014 with the National Urban Design Award with the Royal Canadian Institute of Architects. Amongst others, there were several awards that went to this building. So what did we do on this job? We got involved with the architects very early on. The architects recognized that trying to achieve this goal of theirs would require some expertise. So they hired us very early on to assist with stone selection, design assist, which included approaches on backup and how we were going to anchor the material to the building, how we were going to develop numbering systems to track and control all the materials, quality control program. We had several visits to the quarry to meet with the quarriers and the fabricators, and then we produced the shop drawings, fabrication tickets, and the engineering also did field inspections to ensure that the project was executed properly. So let's start at the beginning with the quarrying and sourcing of the material. The material is the Montclair Danby, and the Vermont quarry is the largest underground marble quarry in the world. It is still entered by the same opening that was opened 100 years ago, and now consists of 1.5 miles of quarries, of paths into the mountain to where they're quarrying the material right now. Material varies as you go through, so the material can be vein cut or flurry cut, which gives a very different look to the material, and it's slabbed in different thicknesses depending on the use of the stone. In our case here, we utilized 5 centimeter material, 2-inch thick. So let's look at going into the quarry. It's very, very interesting. So this is part of the quarry, somewhere about 1 mile into the mountain, and you can see the material here that we were looking at. You can see some of the equipment that's used for cutting the blocks out. Blocks come out in very clean rectangular sizes. Here you can see some other parts of the quarries that have full equipment in there for moving and handling. And there's very, very large caverns cut out in the mountain on the interior. So several visits to the quarry involved a lot of communication with the quarriers, with the architect, what was feasible, what was not feasible. The other very important thing was selecting the materials that had the properties that we needed, physical properties. So that was some limitations related to that. Some of the quarry, some of the materials had fissures and cracks in it, so we couldn't use those areas. So we had to find walls of very sound material that we could procure for the project. Here you can see how they grade the different materials in the quarry depending on color and veining. And here was, you could see the Danby grade pearl, which is the material, one of the materials that were looked at. And in fact, we used the Montclair, which you can see on the upper part of the quarry there. The other very interesting thing with this quarry is right inside the mountain, they've built the full fabrication shop. So the blocks are extracted and they're actually slabbed and polished or honed to the finish right inside the mountain. So the full, they're exported out onto trucks in full slab format, which is really interesting. I don't know that I've visited many quarries in the world, and I don't remember seeing any other one that has a fabrication shop like this right inside the mountain. So here you can see some of the renderings and models that the architects were drawing up to give us the inspiration of their goals, which was shared with the fabricators. And you can see a repeating pattern of the quarry wall because we needed to utilize all the blocks. We weren't able to quarry a large enough area to get a full extent of the quarry wall. So a repeating pattern was what we were trying to achieve. The other thing the architect wanted to do was to create different steps in the face of the wall, again, to try and mimic what's happening on the quarry wall itself, because as you're extracting blocks, there's usually little steps in the different areas of the wall. So the facade was actually stepped in and out as much as 2 inches or 5 centimeters from the maximum point to the minimum point off the anchor. So the anchoring system had to be designed to make these adjustments. So obviously a numbering system and developing a way to track all the materials was very important. So the slabs were all procured, numbered accordingly, and as we move on, we developed a system for the quarriers and fabricators to follow, and obviously had to be reflected on the job site as well. So the other important thing was testing the material. The materials on this quarry here vary quite a bit depending on where it's being extracted from the quarry. So being used on an exterior as a cladding, we needed to understand the material properties that we were dealing with and utilize blocks that fell within the parameters of the physical properties required for the project. So the main test that we did, obviously the flexural strength is one of the most important tests that we need to do in order to understand the material properties in flexure and how far we can span between anchors, and really gives us a measure of the resistance of the stone to wind loads and seismic loads. The other very important test to do is to test the anchor strengths of the material. So we did pull strengths and shear strengths on the proposed anchoring system. So we understand obviously the capacity of the anchor and how much that anchor strength varies. So why are these tests important? I think it's very important to understand why we're doing this testing and why we request testing from architects on projects. Here's an example here, not of this material, but I put these examples together really just to demonstrate the importance of testing and why we do it. So here's a series of flexural strengths, and if we look at material A and material B, the material strengths are very similar in mean. So the average strength, we can see the average strength of material A is 1,018 psi. The average material of material B is 1,006 psi. So if we were to get those materials and those properties alone, and we only get the average strength of the flexural strength given to us, we would assume these materials would be very similar in strength, very similar in characteristics. What we get from doing this type of testing is we understand how variable this material is. Being a natural material extracted from the ground, it's not a manufactured product where we've got very consistent results. We have variability in the stone. So when we chart these two materials and we look at them graphed, we can see the straight lines are the average strength of material A and material B. And I'll just get my cursor out here. So you can see that the average strength of the two materials is very consistent, just above 1,000 psi. We would think these materials are very similar. What we can see though is the material B, how much it varies in strength. We've got flexural strength that failed at 1,400, but we also have some that failed down around 600 psi. The average still came out the same, whereas material A, we have a much more consistent material. So what that does is, when we look at the material properties, we calculate the coefficient of variation of the two materials. This is really a measure of how much does the strength vary? How variable is this material? Which is a very, very important measure for us as engineers to understand how much of a safety factor we need to apply to the material. So when we compare these two, when we look at material A with a coefficient of variation of 7, we would be very satisfied to apply a factor of safety of 3 if it's a granite and 5 as a limestone. Generally, granites are more consistent than limestones because granites are igneous rocks, limestones are sedimentary. A little more variable generally with sedimentary rocks. So these would be the safety factors we would apply on material A, whereas material B, because of the large variability, we would apply higher safety factors. Now, if we look at the graphs, we're looking at a material that has a strength of around 1,000. Applying a safety factor of 3 to that granite, we would be designing somewhere around the 300 psi, which gives us a large safety factor on the blue material here. This one here, material B, we would be applying a larger safety factor. We would be designing down around the 200 level, which makes sure we have enough safety to cover for these low results. So here I wanted to just demonstrate that getting average strength of a material is not enough for us to make an educated, safe design approach to a material. So in this case here, our material was quite variable, and we had a pretty large safety factor, which really predicated the size of the material, size of the slabs that we came up with in our design, and it drove the thickness of the material that we were using as well. So if we look at the shop drawings now and the development of the shop drawings, we can see here one of the elevations we developed. You can see the rectangles that we've used to isolate the different sections of the elevation, and developed an independent numbering system for each one of the rectangles that we developed. So then when we quarried the material, the blocks were all numbered initially, and then each slab, as it was cut through the blocks, was numbered in sequence. So these were all tracked, numbered from block to block, and then slab to slab. And then as these were tracked, we developed a numbering scheme. So again, this is one of those rectangles on the elevation with the slab numbers and the block numbers all indicated. So each piece, when it was quarried and numbered, had the block number, the slab number, and the position indicated. So you can see here A, B, C, D, A, B, C, D. This was slab 2 from block 482, position A, same block, same slab, position B, same block, same slab, position C, and position D. And these were done on each elevation with each block and each slab cataloged and marked. And this was the legend that was used by the installers, but these numbers were also transferred onto the full elevations of the drawing as well. So this was the process that went through, that the fabricators went through in numbering each of the areas. So this was actually a rectangle that comprised the 4 pieces that were being cut out of this slab. And that's the process that went through, and they were marked. It's very difficult to see, but these are marked with a yellow marker, kind of where the cuts are going to be made within this rectangle that consisted of 4 pieces. So if we continue on, here you can see again the elevations that reflect this elevation here on, so that the top piece here is reflective of the top elevation, and you can see down here, again repeating, you can see this break line that happens right across here, one numbering system up here, and then another numbering system down here, which repeats, and these slabs are repetitive on the elevation. We get over to some of the other areas. The main entrance area is another area that we actually built in 3D because of the shape of the pieces. We developed this in 3D BIM and modeled all the pieces, and actually developed all the cut sheets out of the 3D models as well, and the numbering system as well. And you can see here how it looks in the finished condition, and how the actual veining wraps right around the columns and down from the fascia down over the soffit, which they did an outstanding job here of how they did that. So let's get into now, how did we fasten the anchor? How did we fasten all these stones back to the building? So let's look at the approach we took here. When we're looking at anchoring systems, there's several things that will drive our approach. One is, how far off the structure is the stone? Is there insulation? How big is the cavity? How big are the pieces? And what is the structural backup that we're anchoring to? So in this case here, we had a few different conditions to deal with. We had some parts of the building which were all poured concrete backup, and we had other parts that were metal stud backup, light gauge steel framing. In all cases, we had insulation on the backup. Sorry, in some of the concrete areas were uninsulated, but most of the areas had insulation. So we wanted to develop a scheme that was not going to penetrate the insulation as much, and really reduce the amount of thermal bridges that we were creating through the insulation. So our approach was to develop a system where we could bring most of the anchors outboard of the insulation, and penetrate through with anchors at sporadic points, so we don't penetrate through the insulation that much. So here's a typical load-bearing connection. In this case here, we're right up against concrete with no insulation. So what we developed was an anchoring system that would engage into the stone and anchor back to a strut that allowed us adjustment up and down to the installer. The adjustment in and out would be taken up by adjusting the connections to the strut, and I have another detail that I'll get into more detail with you on that. So if we look at the next connection, here you can see that we're anchored back to a metal stud system here, and we're connecting back to a formed channel with a anchor in a similar fashion to the stone. Here you can see the lateral tie-back connection at the top that ties the stone back as not carrying any load. The other anchor, the previous anchor, is the one that's used to carry the load of the stone, and this one here is carrying lateral load only. So we can see when we get to the actual anchors themselves here you can see how they're engaged off the strut, and they're anchored back here to the structure. This is a mock-up panel that was done in the fabricator's shop, just to understand the feasibility and how the connection works. And here you can see the anchor engaged and connected to the back of the panel. So what did that require in the shop? Required ensuring when we epoxy anchors into the stone, we want to make sure that there's no dust, no contaminants on the material. So here you can see that the material's been cleaned with a cleaning agent to ensure there's no dust or dirt on the panel, and then the anchors are epoxied in with the T-bolts that engage mechanically anchor into the stone and also adhesive onto the stone. And this is a good picture that shows how that is. When you're epoxying these anchors, you have to ensure that none of the epoxy fills into the gap here, otherwise it could impede on the connection here, on the engagement of the connection. What we like to do in here at the connection is to fill this with sealant, with a compressible sealant, usually a silicone, that will allow for some cushioning and also pick up any tolerance or gaps in there, that once that sealant sets up, you've got no movement in that connection. Even though there is a little bit of free play in here, the sealant will pick up any of that free play. Now we can see here a few photos on the job site itself. And here you can see the anchor that connects back through the insulation. You can see the vertical struts here, again, all outboard of the insulation. So the penetrations going through, which we're creating thermal bridging, only at these locations where we're penetrating the insulation. Otherwise, the insulation runs right behind the anchors. Here you can see it better up here. And all of the anchoring system is on the cold side in the winter and on the hot side in the summer. So we're trying to minimize the amount of penetrations into the insulation. So here's a few site photos of that. Here we can see the main entrance, and again, the strut system that we utilize to connect into. So really this is where all the tolerance is picked up from the structure, and you want to make sure that once these are set in the exact location that we want in order to receive the stone in the final position. So this is really the part that needs the attention, the surveying, the layouts, to ensure that these are all set. Once these are set in the perfect position, then the stones go in very quickly. It's just a matter of dropping them in place. So when we get involved early, we try and develop connection systems that allow the installer as much adjustment as possible at this location here. So let's to finalize here, I want to share with you the project team that we had a great pleasure of working with. You know, a project like this, in order to execute properly, really requires a lot of collaboration. And we did work very hard together to get through some challenges. The architect had to cooperate with us, with the quarrier and the limitations of the material. Some of the things, you know, weren't, let's call it 100% executable based on the limitations of the slabs in the quarry. But I think all in all, we all really achieved the goal and vision of the architect. And really that required a lot of collaboration. So the architect was fantastic to work with, very engaged in every step of the way. Vermont quarries, right from the quarry people to the fabricators, great to work with. We were involved in every aspect of the project. We worked very closely with Pomerleau and the general contractor, really related to site conditions and some of the challenges on the site. Marble supplier was CIOT, and National Ceramic was also the installer, which is a CIOT company as well. And marble fabricator was done at the quarry by Vermont Marble. Again, the whole team collaborated very closely, which resulted in the great results of the project. So to end, let's just go through some of the photos here that really show the project in relation to some of the other buildings in the area. So you can see here the old cathedral that was purchased and actually became part of the museum as well, and connects into the new modern building at the end, which is a stark contrast to the old historic building. Here's another view from a different angle that you can see it's actually wrapped on 3 sides in the marble. Here you can see a straight on elevation on how that addition ties into the old building. Here's a few photos I took on one of my vacations to Montreal, and had the pleasure of going to see an exhibit in the museum, and just took a few shots while I was there a few years after the completion of the project. And here you can see it in relation to some of the other buildings. There's the 1993 building. Here's the older one. I believe this is the 1913 building. And then across the street, the new buildings that have become part of this whole museum. And there actually is another building that was built after this one here, which is now Pavilion 5. So there's been great expansion of the museum in recent years, which is great. And here you can see some photos of the main entrance again, and how that's all tied in, and ties into the main entrance, actually into the old cathedral. So this is really the only marble part that's independent of the main addition, that ties the 2 parts together and kind of links the old part of the cathedral to the new addition on the other end of the building. So that concludes my presentation. I hate to be doing this virtually, but in the world we live in right now with COVID, I guess it's the next best thing. I wish I could have the opportunity to presenting this in person and field questions, but I've got my contact information here. I encourage anybody that's interested or has any questions related to the presentation, please feel free to take note of the email, and you can send me an email at any time, and I'll do my best to answer any of your questions. I hope you enjoyed the presentation, and thank you very much for checking in and listening to the presentation. I hope you enjoyed it. Thanks again.